Welcome to another series in the expanded concepts of time. In the previous video, we introduced the idea of two universes coupled together with these mathematic operators of divergence and gradients. In these next two videos, we're going to talk about the coupling between these two universes that we introduced. So let's revisit scalar and vector fields. And the question that we're going to look at is which is more fundamental? So on the left-hand side, we have two graphics that represent a positive charge and a negative charge. And these positive and negative electrical charges generate scalar fields, and they're in a location of, say, x1, y1, z1 in scalar space. Now, from these scalar fields that are generated, we can derive a vector electric field at that location. This is derived from the gradient operator applied to the scalar field generated by the charge. So in space, for electric fields, scalars are more fundamental because the vector fields are derived from the scalar fields. Now what about magnetic fields? So we learned that in the physics of electrodynamics, the vector electric field is derived directly from a scalar potential field. The scalar potential field has units of volts and is only dependent on scalar space variables. The physics of electrodynamics for a magnetic field is not so simple, as will be shown in the next few slides. I'll explain how magnetic fields are dependent on the time scalar field. So magnetic fields are always generated from dipoles. Now, those of you that are not familiar with dipoles, that means with magnetic fields, there are always a north pole and a south pole magnetic charge coupled together. They are never independent. So no matter how small you slice up matter, you will always land up with two magnetic charges, a north and a south pole coupled together. In space, magnetic fields are always vector fields because they always have a magnitude and they have a direction. Now, what happens when we apply change in the form of time to an electric monopole charge? When we apply change in the form of a derivative, d dt, to a charge at a location x1, y1, z1, then we get dx1 dt, dy1 dt, and dz1 dt, or the motion of this electric charge in 3 dimensions of space. So what are the results? Well, from the bottom, we can see that the moving electrical charges generate an electrical current. And the moving electrical charges also generate a magnetic field surrounding this electrical current. So applying time to electric monopoles produces a magnetic field. Without time, it is just electrostatics, an electric charge not moving in space, but still with an electric field. A magnetic field from a magnet is produced by the motion of the electrical charges within the atomic particles in the magnet. All these magnetic fields combine to generate the magnetic field we measure outside of a magnet. If the electrical charges within the atomic particle could not rotate, that is, there was not the application of time to generate this motion, there would be no magnetic fields. The same is true for electromagnets, but here the time generates the motion of the electrical charges in the form of an electrical current, as we learned in the previous slide. So there's a key fundamental difference in how electrical and magnetic fields are generated. Magnetism is coupled directly to time, and static electrical fields do not depend on time. So as the title of this slide says, magnetism is coupled to scalar time. When we apply change in the form of the derivative of time, d dt, to a magnet to move the magnet through a coil of wire, an electric current is generated in the wire. We learned from previous slides that an electric field in motion generates a magnetic field. The application of time to generate motion in space generates these two electromagnetic fields together. Let's revisit the relation of scalar space to scalar time. And in the matrix of time, we'd gone through this example where we had a driver who's traveling a distance of 3 miles in a travel time of 5 minutes. So the speed of 3 miles distance in 5 minutes works out to be 36 miles per hour. Now, what happens if the driver decides to go up to 72 miles an hour? They can do that in two ways. Either they can cover 6 miles in the same 5 minutes, or they can cover the same 3 miles in 2.5 minutes. So 72 miles per hour, or kilometers per hour for the rest of the world, but I'll stick with miles per hour for now, can be reached by either increasing the distance by 2x or reducing the time by a half. So what you notice is that distance space is equivalent to 1 over time. For instance, 2 times the distance has the same effect as 1/2 the time. 3x the distance is equivalent to 1/3 of the time. 10 times the distance is equivalent to 1/10 of the time, and so on. So time is equivalent to 1 over space, and space is equivalent to 1 over time. So we can say that time and space have an inverse relationship. And you can see that motion is the phenomenon that links space and time together in this inverse relationship. In case you missed the Matrix of Time video series, this reciprocal relationship of space and time is the basis of Dewey-Larson's reciprocal system theory. So in the previous video of this extended concepts in time, we had talked about how you could use mathematic operators to transform a scalar field to a vector field and a vector field to a scalar field. So we could take the scalar time and apply the gradient to get vector time, and we could take vector space and apply the divergence to get scalar space, and obviously we could do the reciprocal when we're going from 4 time back to 4 space. In this video series, we learned that scalar fields are more fundamental than vector fields. So if we take just the scalar time of 4 space and scalar space of 4 time, we see that there's a reciprocal relationship between the scalar time field and the scalar space field. And so we're going to just deal with these scalar fields because they're more fundamental, and the vector fields will be derived from these scalar fields. So just to summarize, on the bottom there, we have scalar time is equivalent to 1 divided by scalar space, and scalar space is equivalent to 1 divided by scalar time. So for completeness, we show, again, these 2 coupled universes, and we show primarily that we show fundamentally that scalar time and scalar space are related with a reciprocal relationship, and then from these vector fields of vector space and vector time are derived from these scalar fields through the divergence and gradient operators. So we go back to the relation of scalar space to scalar time. And we established that motion is the fundamental process which defines the relationship of space and time in this reciprocal fashion. So on the left-hand side, we have our familiar 4 space, and we have scalar time. And on the right-hand side, in orange, we have the alternative universe, 4 time, with its scalar space. And these are represented as 2 balloons. This is a common format to explain the expansion and contraction of scalar times in the reciprocal system theory, so I'm going to use it here. But here I'm just taking 2 of these balloons and I'm tying them together. So there's a constant amount of air in both these, and there's a little tube between these 2 balloons that the air can move back and forth. So now what happens if, due to some force, the scalar space balloon is forced to contract? What it will do is it'll force some of the air that's inside this balloon into the scalar time balloon, and the scalar time balloon will start to expand. And in the reverse, if scalar time contracts below its normal state, then scalar space is forced to expand. And you can see this reciprocal relationship, that as one of these scalar fields starts to contract, the other one expands, and as the other one contracts, the other one is forced to expand. So it's this inverse relationship that we learned about space and time through motion. Here I present how I find it easy to visualize this, and maybe it'll help you, I'm not sure. But these 2 universes are coupled via energy in the form of matter. Now, they are the same thing in that energy is equal to mass times the speed of light squared. But the key difference is that we can see matter, but we cannot see energy. So invisible energy via visible matter is the conduit that generates the expansion of one universal scalar field and the contraction of the other universal scalar field. So hopefully this will help you visualize this a little bit more. You can imagine again these two balloons, and there's a tube, and the tube is really invisible energy or visible matter. Now this might be obvious to some of the more technical types, but the total amount of expansion and contraction between scalar space and scalar time is conserved. So just a quick diagram that shows that as scalar space contracts, scalar time expands, and as scalar space expands, scalar time contracts, and the combined amount is always a constant. Okay. Because of this conservation, what happens is that as soon as scalar space begins to contract, scalar time begins to expand, and so these two move in opposition to each other. So this diagram also shows a different way of scalar time and scalar space. So far, I've shown them as two separate spheres, two scalar fields that are separated. But I did that just because it's easier to visualize the relationship of these two scalar fields. But the way I think of this is that these two fields are interleaved. So they are interspersed the same way that air is interspersed in water. Think of it that way. You can think of bubbles suspended in water. These two fields are completely interleaved and overlapping each other. And so while one is expanding, the other one is contracting. It's all done in opposition to each other and done through this conduit of matter. Now, all our matter in the universe is in constant motion. As we've mentioned before, these two fields are tied together. A good example of how this is tied together is through photons, because photons move at the scalar speed known as the speed of light. This is a relationship of 186,000 miles for every second of time. So what do we know about our universe? Science has measured that vector space is expanding in all directions at an ever-increasing rate. Dark energy and invisible and undetectable energy is theorized to generate this expansion of matter in vector space. It is expected at some point in the future this expansion will slow down, and then the space will start contracting because gravity will become stronger than the dark energy that is causing this expansion. At some point again in our future, our universe will reach the other limit of maximum contraction, and dark energy will overcome gravity, and then our universe will start expanding again. So you can think of this expansion and contraction of space like the breadth of the universe. So let's pull all this information together in a new way to visualize our universe. If our vector space field is expanding in 4 space, then scalar space field in 4 time is also expanding. If the scalar space field in 4 time is expanding, then due to the reciprocal relationship between the fundamental scalar fields, the scalar time field in 4 space is contracting. This means any matter in 4 space that is related to time, to the scalar time field, will be in opposition to that part of the matter that is related to the scalar space field. So if matter is more correlated to the scalar time field than to the scalar space field, it will contract. If matter is more correlated to the scalar space field than to the scalar time field, it will expand. The amount of expansion or contraction would be defined by motion, the relationship of space to time. So let's talk about inertia. Let's assume that a portion of the matter that is at rest in one universe, we'll say the green universe, has a force that is applied to this matter to get it in motion. Immediately a force in the orange universe will work in opposition to moving this portion of the matter from rest. This would be true if the portion of matter were in motion in the green universe and you wanted to slow it down by applying a braking force. There would be an oppositional force on the portion of this matter in the orange universe to keep it going. So motion in 4 time would manifest as inertia in 4 space. This inertia would be identified as mass in 4 space. Dewey-Larson says that inverse motion in 4 time is mass, that is, time cubed divided by space cubed. He defines energy as inverse velocity, that is, time divided by space, so mass is motion in 4 time, or energy in three directions of vector time. Scalar motion, see the speed of light in electrodynamics. We started off with electrodynamics when we started this video, and I am wrapping around and coming back to touch base here, and you'll see why. So far we've discussed the speed of light as the ratio of space to time, and specifically the reciprocal or inverse relationship of space to time. The speed of light was determined by Maxwell as equal to 1 over the square root of the permittivity times the permeability. So what are these parameters, epsilon 0 and mu 0? So permittivity is epsilon 0, and it defines how much energy is stored in the electric field. It's also used to calculate the force due to an electric field. If the electric field is in free space, permittivity is defined as epsilon 0. And epsilon 0 is equal to 1 divided by c squared times mu 0. So again, we see this reciprocal relation. Now, permeability, mu 0, defines how much energy is stored in the magnetic field. It's also used to calculate the force due to a magnetic field. And if the magnetic field is in free space, permeability is defined as mu 0. So the speed of light is not only a reciprocal ratio of space to time, but it's a reciprocal relationship of the energy stored in the electric field to the energy stored in the magnetic field. So takeaway messages. Scalar fields, like potentials, are more fundamental than vector fields. The relationship between scalar space and scalar time is reciprocal. When one expands, the other contracts. This can be visualized as the breadth of the universe. Matter exists in both 4 space and 4 time, and therefore is affected by both these motions of scalar expansion and contraction. Our universe of vector space is expanding, which means that scalar space is expanding. Due to the reciprocal relationship, the universe of vector time and the scalar time fields are contracting. This opposition to motion by these scalar fields could account for inertia and the effect of gravity, both of which are linked to mass. Larson has defined mass as motion in 3 dimensions of time. The speed of light defines both the relationship of space to time and the relationship of the electric fields to the magnetic fields. In the next video, I'll discuss other implications of these 2 coupled universes. If you want to hear more of the Matrix of Time videos, this expanded one that you're listening to, please subscribe below to be notified of new presentations. You can also go to my website, www.multidimensionaltime.com, and there you'll see that there's a book available. There's also some technical white papers, and all the links to my videos that are available on my YouTube channel can be found on my website. Okay, thank you very much.